Hey, what's up, guys? This is Jung. So this time, 1673. Find the most competitive subsequence. So this is today's daily challenge. Mm, so you're given like an integer array, nums, and a positive integer k, and you need to return the most competitive subsequence of numbers of size k. And an arrays. Okay, so that's the definition of subsequence. I think everyone already knows that. And then the definition of competitive is the basically it's the lexicographically smaller subsequence. For example, if this 134 and this 135, since this one 134 is smaller than 135, right? Compare the values one by one, and then the smaller one we call it more competitive. So actually, so and the example uh, we're given here is like that with all the possible like subsequences. We just need to find the smallest, right? That's what it's called most competitive. When in this case, is 26 is the smallest among all of kind of subsequence. So and then the problem comes down converts to which we need to find the smallest subsequence whose length is equal to k, right? Mm, yep. So and that's basically the idea. And if we take a look at this example here, right? The let's say we have example 2 here, and the answer, right? So the answer is like uh 2, 3, 3, 4. So we have 2 first, and then we have 4. We have 4, but then the next one is 3. But which means okay, so 3 is smaller than 4, which means that we can replace this 4 with 3, and then we have another 3, 3, 5, and then 4 is smaller than 5. That's why we can just replace this 5 with a 4. And then we have a 9, but 9 is greater than 4, and 6 is also greater than 4. That's why we have this answer 2, 3, 3, 4. And similar for this one, right? So we have 3, 5, and then we have 2. 2 is smaller than 5, so we can just move this 2. Basically, we can replace this 2 to both 5 and 3, and then we have 6. So by looking at this one, actually, so this is like the very similar to like a monotonic queue, right? So basically, we're trying to maintain like an increasing queue, and every time when we have like a greater numbers, a bigger numbers here, and if we saw like a smaller numbers, basically we're trying to pop that greater number out because remember our purpose is to find the smallest subsequence. Okay, but we cannot just blindly pop all the numbers that's who is uh, greater than the current number, because we also have like this kind of k limits. So for example, if we have like what if we have like let's say 9, 8, 7, 1, and 3. Let's say if this is the numbers and the k is equal to 4, right? So we have 8, right? Sorry, we have 9. Uh, so yeah, so we can use this example. So we have 9 here, right? So and then the next one is 8. So 8 is smaller than 9. That's why let's say we have an answer here, right? At the beginning we have 9, but the next one is 8, so we can just remove 8, replace pop this 9 and we push this 18. But the next one is 7. But can we pop 8 and then push 7? We can't, because if we pop 8 out from the answers, then we only have 3 numbers left. It won't be even be able to make like the substring of k length. So that's why, in this case we have to just append everything in the end. So that's why the answer for this one is going to be 8713. So now I guess we have our complete algorithm. So the algorithm is going to be, every as long so the first one is that, let's say the current number is smaller than the top one in our stack, and the remaining numbers of is enough to make this length k subsequence. Then we can pop the current one. We can pop the top element from the stack. Else we just need to stop. Mm, yep. And another like condition we need to consider is that, let's say we have like this one, 1, 2, 3, 4, 5, 6. And then for this one case, let's say it's also equal to 4. So for this case, we basically we keep uh, pushing into this answer. We have 1, 2, 3, and 4, right? Now the next one is 5, but we cannot push it into the answer anymore, because the limit is k. So we only push into the answer when the length of the answer is smaller than k. Yep. And right, but let's say we have like the next one. Let's say the last one, instead of 6 is 2, right? So then our algorithm will be like this. So we have 1, 2, 3, 4, and then the 5 is greater, and so we will not try to pop this one, and since the length of the answer has already reached 4, and then we basically will skip this 5. Now the last one is 2, right? So the last one is 2, and 2 is smaller than 4, and that's why, and the 2 is enough to pop only one number out. That's why we're gonna replace this 4 with 2 here, and our final answer is gonna be 1, 2, 3, 2. And we cannot keep popping because we don't have any numbers left. That's why we can only pop one number out. And yeah, so basically this is like a greedy uh, plus you can call it an increasing Q algorithm. And yeah, I think let's start coding. So the code is pretty short. We have a length of numbers, right? So for I.num in enumerate and nums. So while the answer is not empty and the current number is smaller than the top one in the answer, and then we'll try to pop. But before doing the pop, we have to check if the n minus I is greater than the k minus length of answer. So here n minus I gives us the remaining numbers, including the current number, right? That's going to be the total numbers. If the remaining number, including the current number, is greater than the remaining slot in the final answer, right? Comparing to make a length k subsequence, then we can pop the answer, the first one, right? Else we simply break. and then we just need to do a append, right, to the numbers. But like I said, before doing the append, we also need to check. We only append if the length of the answer is smaller than k. Then we do the append. So, and in the end, we just simply return the answer. Yeah, I think that's it. Okay, if I run the code, accept it. Yeah. So for the time complexity, right? So we have a for loop here, and then there's a while loop here, but since we'll only be pushing uh and pop the each number at most 2 times. That's why so this while loop will not count, add another layer dimension of time complexity. So the actually the total time complexity is the O of n, right? And the space is also O of n, space and time. Yep. Yeah, I think that's it, right? I mean, I think for this problem, it's not that hard, right? That we can start with the generic case, which is like the example 2 here, right? Then we just basically process numbers one by one, and every time when we find the current number is smaller than the previous one, then we'll just try to replace that. Also, we need to check the condition if there are like enough numbers left. If we can afford to pop the current number. If we can, then we'll of course pop the number because we're looking for the smallest number. Otherwise, we break. And here is the do the append. Cool. I think that's everything I want to talk about for this problem, and I'll just stop here. Uh, thank you for watching this video, guys. Stay tuned and see you guys soon. Bye bye.